Hello everyone. Today I'm gonna teach you how do I solve problem 310 by tree dynamic programming. And a disclaimer is that this algorithm is not come up by myself. It is the second most upvoted solution in the discussion forum. So yeah, let's get started. So basically we will have a tree roots at 0. And we will claim that we can compute dp at I. That is the longest, or you can say the height of a tree that is rooted at I. You may wonder why we can set our roots at 0, but we can compute dp at I in O log or in O n, and this is why this is why I record this video, because I want to tell you how this idea works. Okay, so let's keep going. So the one of the trick is that for each node I, we will gonna store two values. One is highest I and second highest I for each node. Okay, so let's give some examples. The first example is that highest 0 will be 3, because we will have two choices here. We can walk to our left child, or we can walk to our right child. So the left hand side can give us the highest, so we will store 3 in the highest 0, while the second highest 0 will be 2. Notice that you may wonder, you can step like 0, 1, and then 3. But in this case, we will set it to 2 because we only have two choices. So it's like highest over its, in this case, 0's children, and second highest over 0's children. So you can notice that 0 only has two children, so it can only have two choices. So, and then we can see that highest 1 is 2, and second highest 1 is 2, because from 1 to 2 the height is 2, and 1 to 3 the height is 2. So let's go through the second example. The second example is that highest 0 is 3. You can see that 0 has two choices. Either goes to its left child, which is 1, or its right child, which is 3. So it will give 3 here and 2 in the second highest 0. So that gives us some intuition. The intuition is that, let us say we have already defined dpi be the height of a tree rooted at I. Notice that our setting is that we can always compute dpi from DFS. So let's say we can solve it in O n time. Even we have rooted our tree at 0, we can compute every node. For every node, we can compute the height of a tree rooted at I. Let's say we can only go through for like in constant iterations, and we can know this number. So let's assume we have already computed these two variables I have already introduced in advance by DFS. So it will be very easy to know a simple case like dp0. We can just use highest I because this tree is already rooted at 0. So we can just use highest I because among the children of 0, we can only have highest I from like 0 to 1 of each child, and then like for example like this case, you can go through the rightest child to get the highest I. Then we will wonder, how about computing dp at I? Let's just assume we know the longest path from J to other nodes other than J's descendants. So in this case, like J to other nodes other than its descendants. Let's say we know this number. It will be very easy to see that we can compute dp at J by max over highest J. So in this case, highest J is from J to the one of the descendants of I, and over the longest path from J. You know that if we root this tree at J, you only have these choices, and basically highest J will just compute all the possibilities from J to the nodes of the descendants of J, and then this number can give one more choice, because if we root the tree at J, you have these choices. J's children will be these nodes. Okay, so dpj turns out to be easy to be computed, and later one remaining question becomes, then how can we compute the longest path from I? Let's say we already know this number, but if we gonna compute dpi, we will also need to know the longest path from I. That's I to a node other than I's descendants. Let's say I maybe go this path, maybe go this path, maybe go this path, but we do not know. So how can we compute it? It turns out it is also easy to see. Let's assume we have this case. If highest I plus 1 is equal to highest J, so it's like J's choice, J's children will be I, and then later is children and the right sibling and the rightest sibling. So the longest path from I should be the second highest J, and max over second highest J and the longest path from J, because we already know that from J passing through I to its descendants, it will give us the highest. So we have to eliminate that choices. So we can only choose second highest, because second highest will choose a second highest path, a second longest path passing through a node other than I. Okay, so that would be easy to be computed. And then we will see a second case. A second case is that highest I plus 1 is smaller than highest J. Let's say this is shorter and this is higher. So we will have highest J and the longest path from J. We will max over these values, and then notice that we have to plus 1 because this edge. So you can see that because we want to know the longest path from I either to somehow other nodes other than the descendant of I. So this basically highest J basically compute all the possibility among the siblings of J other than I, and this will give one more choices, because this path is also passing through one of J's J's children. You can know that like this there is a node here that is also J's child. Okay, so there are still one tricky thing is that how can we compute the longest path from 0? You know that we define the longest path from 0 is the longest path from 0 other than from 0 to a node other than the descendants of 0. So basically it is just 0. Okay, so that basically my workthrough will have already explained all the details of this algorithm. If you want to know more about how do I actually write this program, you can see my GitHub's code down in this video's description. Okay, that's all. If you have further any question, you can just leave a comment. I will reply you as best I can. Okay, that's all. See you next time.